All right. Good morning, everybody, and welcome back. This is what we're up to today. So we're talking about the advection equation. And like last week, we're going to start with a lecture to kind of give you some ideas of what the advection equation is and how it's used. This is, last week we saw the diffusion equation. That was the first kind of equation that we encountered and looked at in any detail, and the same will happen this week, similar kind of thing. And next week as well, we'll talk about the equations of viscous flow in rock and apply that actually to ice to look at glaciers. So this is what's going on. Before we go into the lecture and then the kind of preview of the exercise, I wanted to ask, how are things going with this exercise number 10? Are there any big problems, or is this seeming like it's a bit better than the previous ones in terms of how things are going? Yeah, mostly? Okay. That's good. I tried to sort of focus a little bit more on making that exercise not require too many new things at once and be a bit more structured, so I'm glad to hear that it seems like that worked in that direction. So here we are. What we'll do, again, is we'll start with a little lecture to introduce the advection equation, and in this case we're going to end up applying it to looking at how bedrock rivers erode. There are lots of different things we could do with the advection equation, but this is kind of a nice example that lines up with what we do in the exercise for this week. And hopefully by the end of this lecture you have some idea how the advection equation relates to river erosion. So the goals basically are twofold. One, I want to introduce the advection equation, and then secondly, discuss how you can apply that to understand erosion of bedrock rivers. And so we have to start by talking about what advection is, and it may or may not be a familiar term. It's a bit hard to say. If you've done anything in geophysics, you've probably heard advection before, but or if you've taken any kind of heat transfer, geothermics course or something like that, you would have heard advection. But it basically refers to translation of some quantity. And in this case, what you're looking at is an animation of flow in the mantle, and the colors here represent heat. So the red colors are relatively warm, blue is relatively cold, and you can see things that look like plumes and sort of sinking plumes of material where you have cold, dense rock that's being basically subducted down into the mantle, and in other places relatively warm upwellings of rock. As the rock is moving, it's carrying heat with it. So in this case, that's what's being advected. You have the physical movement, the flow of the rock in the mantle, and as the rock flows, it carries heat. So this is just kind of one example here of advection in the context of heat transfer. We could look at that in detail, but we won't do that for the exercise this week. But you can use the same equation. Just as a reminder then for what we did last week, this is the diffusion equation, or the parts of the diffusion equation that might look somewhat familiar. We didn't spend a lot of time talking about the mathematical representation in lecture, but the notes on how to solve the diffusion equation showed things like this. And I made a point of mentioning the kind of two components of the diffusion equation, the flux part and then the conservation of mass part. And so here you have some flux of material. If we apply it to hill slopes, this could be some flux of sediment or soil that's moving down a hill slope. And it's proportional, that flux, to the slope. So dH over dx is just the slope of the surface in this particular example. And we also saw then the conservation of mass equation, where we related the change in that flux over some horizontal distance to a change in elevation. So we saw that when the elevation would go down in the case that the flux is high, because that means you're losing more mass locally than you are gaining. And so if you think about that in terms of what would happen at the Earth's surface if you remove more mass than you bring in from somewhere else on the hill slope, you'd expect the elevations to go down. And so those are the two pieces. And again, this is something, if you're looking to refresh yourself on how the diffusion equation works, you can look at the notes from last week about solving the diffusion equation. So in the notes, we basically put these two pieces together. I didn't go through it in detail last week, but basically you can see the Q here, the flux, and you just plug in that Q here where you have this dq dx term. And when you put those two equations together, you end up with this. That's the sort of classical form of the diffusion equation. And that's about as much as we need to say about the diffusion equation today. I don't know kind of how familiar you all are with derivatives and second derivatives and things like that. But here we just have this change in elevation with time, dh dt, being related to the second derivative of elevation over some horizontal distance. So if you're at all mathematically inclined, this is basically representing the curvature of the surface, and we'll see how that works in a little picture in just a second. But this is our diffusion equation, and this is what we did last week, so we're not really going to focus too much on that going forward. But what I do want to do is contrast this diffusion equation with the advection equation. So here are the two side by side. And you'll notice they look quite a bit like one another. First off, we have dh dt on both equations on the left side. This need not be h. It could be something representing energy or temperature or whatever. But here we'll keep it in the context of height of the elevation surface. So we have dh dt on the left side in both equations, and we have something related to the change in height divided by some small horizontal distance. But here we have only the first derivative compared to the second derivative in the diffusion equation. And we have some slightly different constants out in front. So these are our main differences. So the change that we have on the left side being related to now a first derivative rather than second derivative of the height or whatever it is you want to represent, and a coefficient out in front. This was the diffusivity last week, and this week it's just called the advection coefficient, and it has different units. So you could probably see that just from the fact that this is dh dt over here, and if we have a second derivative on this side, the units of this thing must be different than they would be for the same equation with the first derivative on the right side. So here we have units of length over time for the diffusion coefficient, and I'll point it out now, and I'll probably make a point of saying something later that this is length or distance over time. This is basically a velocity. So it may not make sense just yet what this velocity means, but this advection coefficient has units of velocity in the case that we look at something like a hill slope. So we can illustrate how these two equations look different or how they behave differently here by looking at what happens to some hypothetical river channel profile over time being acted on by diffusion in this case. So this is basically kind of a cross-section view of some river flowing down over some sloping topography. And so there's kind of a very gentle gradient or gentle slope up here in some upper reach of the river. And then the sort of river channel gets steeper, and then it gets less steep again. So do you have a picture in mind of how that looks? Because it kind of makes a difference if you have a sense of what I'm talking about now or not. So if I talk about a river channel profile, does that make sense? Yeah, I just can't tell like whether you guys are used to looking at channel profiles or not. If it was a profile of some, the surface of the Earth or something like that, you'd have no problem. Like if we just took a cross section through the Earth and saw that there were some mountains, okay, that's easy to see in a profile view, right? So all we're looking at basically is the equivalent thing that if we used to look following along a river, let's say we got a river that's flowing just perfectly in one direction, and we just look along the length of its flow at here, the sort of elevation of the river channel as you go from some high place, flow down a sort of steeper bit, and then down to some lower elevation part of the river channel. That's the picture. Yeah? So, if we assume that diffusion is the way in which this river channel is evolving, because as water flows along this channel, it's going to change the elevations. What would happen here at time 1 to time 2 is you see that this area up here where the change in slope is most rapid, so where it goes from being flat to being steep, is the place where you see the most elevation change. And same thing happens down here, where it goes from being steep back to being flat. You see the biggest change in the elevation of the river between time 1 in pink and time 2 in red at those locations. If you remember that this diffusion equation is related to curvature, here the curvature is high and negative, so it's curved downward or concave down. Here the curvature is high and positive. And so here what you see is where you have negative curvature, the elevation goes down. Where you have positive curvature, the elevation goes up. So that's what happens if you have diffusion. And if you go through time once again, this basically similar process continues until you end up with basically a continuously fixed slope from one end of the river to the other. The other thing that's worthwhile to note here, and it's maybe easiest to see if we go back just to having two channel profiles, is that because of the conservation of mass that we assume with the diffusion equation, any place where the elevation goes down up here is balanced by elevations going up somewhere else along the channel. So the mass is conserved from one end of this river channel to the other. So if you erode up here, you deposit sediment down there. This is basically what happens in what you could call alluvial channels. So channels where there's sediment in the river and it's able to move around. You see sediment tends to be eroded in places where you have transition to steep parts of the river and deposited where the river flattens out. And you've probably, it's maybe not so easy to see locally. I don't know, I haven't been to Lapland to know whether there are nice alluvial rivers or not. But if you've been any place mountainous, you'll see that when you come out of the mountains, you get these big parts of the river that are very wide and just full of sediment, gravel, and cobbles and things like that. Just the river's got a lot of power when it flows down out of the mountains, and then when it flattens out, it can't carry the sediment and it deposits. So in many ways, this is like that kind of river system, where you go from having the power to carry the sediment to not having the power to carry sediment and depositing it. That's what happens with diffusion and the diffusion equation from last week. But like I said, we're talking about advection this week. And so here's the same channel profile, sort of not very steep up at the top, goes down a steep part, and then gets flat again toward the bottom. And what you see if the river is being, or if its channel profile is being evolved by advection, is from time 1 to time 2, the shape of the channel profile doesn't change. It just moves horizontally with time. And in this case, the rate at which it would move would be this constant c. Remember, this is a velocity for the advection coefficient. So that basically determines here how this river is moving through time. So what you would see if you think about it in terms of a natural landscape is a river that's eroding into some higher part of the landscape. So if this is some plateau or something up here, you'd have the river eroding into the plateau, and the shape isn't changing. It's just moving horizontally inward as it erodes material and it moves away. There's no, and I think maybe I make the point here, there's no conservation of mass in this case. And I guess you can probably see that. We erode quite a lot of material between time 1 and time 2 here, and it's just gone with the advection equation. We're not worried about what happens to it in this particular case. The assumption, if it's a natural river, is that it gets into the river itself, and the sediment's just flushed out of the area, and wherever it gets deposited, we don't care about it in this case. This applies to bedrock channels, and normally where you have bedrock river channels are places where the landscape is pretty steep. So oftentimes there's not really any sediment present, and so you don't really care about what happens to the sediment because you're just assuming it's going to be too steep to sort of remain within this part of the river if it's a bedrock channel. So I guess maybe this gives you some idea of how these two equations are a bit different from one another for diffusion and advection. And we'll go now to take one more look at how the advection equation works. The whole point here, of course, is to sort of understand what is yet another kind of fundamental equation that's used in many different parts of earth sciences and other natural sciences. But here we have basically the same kind of my very simple cartoon version of the same river channel profile, where here it is basically flat, then there's a slope, and then it's flat again. When you have advection as the process you model to change your river channel profile, what you see is at any location, for instance, here on the landscape, between, this gray line, which might represent time 1, and the dashed line that would represent time 2, we see the river channel basically shift horizontally, like we saw in the other picture. The change here is basically this rate of movement from the advection coefficient times time. So if that's a velocity times time gives you a distance. And that distance then would be represented by this arrow here. So that shows how much the river channel moved horizontally. And in that same time, the change in elevation then would be represented here by this DH, the blue arrow. And all of the components that we need here are in this form of the advection equation here. If we put this dt over on the other side, we get c times dt, which gives us the displacement. And then that's multiplied by the slope. And of course you can see that, depending on how steep this is, if you move horizontally some distance, that's going to change how much the elevation would change. So if it was a shallower slope, for instance, you'd see less change in elevation. If it was a steeper slope, you'd see more change in elevation. And if you go up here, if you move some horizontal distance in the flat part of the channel, the elevation doesn't change at all, because there is no slope. It's 0. So when you multiply it by this slope term here, you get 0, so you have no elevation change. So this is the kind of simple view of how things work in river channels, and I say that not to scare you that nasty things are coming, but more to say that this is perhaps an oversimplified view of how river channels work, because the concept works. We model most bedrock river erosion using an advection equation, but it's not quite in this form. So that's what we're going to move to now. So we're going to look here at examples of bedrock river channels. Here's a nice picture from Jasper National Park in Canada. I didn't take the photo, but it's a nice picture of a typical bedrock channel. This is a quite steep one. But what we see when we look at natural bedrock rivers is something that we can model using an advection equation, but one where this coefficient of advection varies with space. So it varies along the length of the river channel. And we'll see how this works in just a second. And again, we're not talking about places like low down in some drainage basin like we have here at the outlet of some river coming out of the mountains, where again you see this nice braided river system with tons of sediment in the river, much more sediment than the river can move. So you have large amounts of sediment being deposited, and there's obviously not much bedrock erosion happening here because there's so much sediment on top of the bedrock that the water simply can't get in there. But if you go to steeper places, this is the Kali Gandaki River in central Nepal, and this is not even necessarily one of the steepest parts of the river, but you have some boulders in there, but more or less you have water flowing over bedrock, and most of the sediment is being, it's in transit in this river system here. So, and here you formed kind of a nice steep river gorge as a result of bedrock erosion by the river system. So we saw this picture before of the horizontal movement of some bedrock river channel through time at a constant rate c in this case, because that's what we were starting with. And my question for you is, do you think that this works in real bedrock rivers? Well, I guess I've kind of already alluded to the fact that it doesn't work in real bedrock rivers. But what I can ask you is maybe what might affect this rate of horizontal erosion of the rivers, or sort of incising into some landscape. What kind of things might affect how efficiently a river could erode into a landscape? Do you have any ideas? Yeah, so, right, the bedrock erodibility, that's a good one. Yeah, like the sort of the base level. Yeah, absolutely.
Water flow rate.
Yeah, so that's a big one, right? The amount of water in the river, because there's, if you start to think about these things in somewhat mathematical terms, if there's no water in the river, there's no river erosion. And the more water you put in there, of course, whether it goes up continuously with more river water you put in, it's not necessarily linear, but yeah, the amount of water in the river is going to matter. There's one other thing that might be important in terms of erosion efficiency for a river. So we got how erodible the bedrock is, the base level, how much water's in the river. It's one other thing that might determine how quickly it's going to flow. Yeah. So the slope, right? So, of course, if it's a horizontal, well, I mean, I don't know if you want to view a sort of river with no gradient with a lot of water, but a lake would essentially be something like that. It's not moving because there's nothing to drive the water to flow against gravity. So we got the important things here: discharge, or the amount of water in the river, slope, and the bedrock strength. Those are the three main things, and of course the base level will come into the slope in some respects. So these things are all going to vary with space, right? As you go up a river, you expect to get less and less discharge because you're collecting water from smaller area as you go upstream. The bedrock strength may change, of course, because you might go from flowing over granite to some limestone or shale or something that's much more erodible. And of course the slope also will change, and that's probably makes sense. So are these constant? No. And that's the reason why this doesn't work. So we'll cross this guy out, and actually we are still going to use the advection equation. I should probably just cross out the c, because we're just not going to assume a constant rate of advection. Instead, we're going to take the same equation, so we still have dH dt over here, we still have dH dx over here, but our c has been replaced by this stuff. So now we have this kf, that should be a subscript, but that's more or less a material property that's related to the erodibility of the bedrock. W is the channel width, and Q is the discharge. And these things relate to one another, that you can imagine if you take a lot of water into a narrow river channel, it's very powerful in terms of its erosion. If you take the same amount of water in a much wider channel, it doesn't erode as efficiently. So those things trade off. But there's most of our terms there, and this dH/dx is our slope. So those are the things we just saw as being important. And now we can consider that these are going to vary in space. And this is what's called the stream power erosion law. I don't know if anybody's heard of this one before or seen it in any way, but it's probably the most commonly used model for simulating river erosion in mountainous landscapes. So this is a very common erosion law. This is not really the most common form of it. So we're going to go to using a slightly different form of the same erosion law. It looks quite a lot different, but it really isn't that much different. It's just rearranged so the terms look a little bit more like this. So again, we'll keep dH/dt, change in elevation with time over there on the left side. We're going to replace this kf over w with a big K, and the big K is the garbage can. So it accounts for lithology, climate, channel geometry, sediment supply. I mean, whatever you want. That is the one factor that accounts for a lot of different things in any natural river. Discharge we replace by area. So this is the area upstream in the river. And the reason that we do that is if we assume that the rainfall is uniform across the river, then we can assume that the discharge goes up as a function of the drainage area. So as you drain more and more of the landscape, your discharge goes up. And this M then is a power law exponent. That kind of determines how that drainage area and discharge scaling works. So normally it's something like the square root of the area is how you see the discharge goes up, but it's there are different models for this. And actually you'll play with some of those in the exercise for this week. S is the slope, so it's basically the same as dH/dx, but I don't know, maybe this is more appealing to the geologists to get rid of the differential terms and put in just one S. But then S again also has its own slope exponent. And these things are determined from experiments and from observations in nature, what the values of M and S are. So this is kind of the much more common form of the stream power erosion model. And in fact, in some cases, people even replace the A by something that's called Hack's law. So it's just the distance from the drainage divide to some power 5/3 as an approximation for how most river drainage area increases. So for simple models, in fact, for what we'll do today, we'll use this Hack's law, where we just assume that area goes up as the distance along the channel to some power 5/3. And again, that's somewhat empirically derived number. So this is our erosion equation, and now you get a chance to test your might, so to speak. If we consider this erosion equation, we're going to use this in the exercise this week, so you get quite familiar with it. But the question here is, what shape do you think your river channel might take with this erosion law if you start out with some initial just constant slope for your topography? If it was undergoing diffusion, this wouldn't change with time. But here we have an advection equation. This is going to change from being something like this with a constant slope to something else. And you might look at this thing and say, well, I have no idea. I don't even want to begin to think about how to guess what shape this is going to be. And what I'd like you to do is just don't worry about K. K is a constant. You've got this area and you've got this slope. And initially, the slope everywhere is going to be constant. And then you've got this area term in there that is going to change. So if this is your hill slope and the area is increasing with respect to the highest point, right? So it's 0 up here, and as you go downstream, the area that you drain gets bigger and bigger. Do you have any idea what the shape of this thing might look like through time? And if you want, you can kind of talk to your neighbors for a second. We'll come back to looking at this, but I'd like to take a minute just for you to think about it before we go to the exercise where like the computer's going to do it for you and you don't have to think. I'd like you just to think about it for a second, what you think might happen. And if you have the lecture slides, please don't go ahead one slide yet. The one other thing I'll say just to help with your discussion is we're assuming an uplift rate that's constant everywhere. And so what should happen is that this river is going to try to balance the rate of uplift by erosion. So that's the one other thing to consider. It might not help, but that's the one other part to have in mind. So yeah, just talk about it for a couple minutes, and then we'll see what we come up with. So yeah, let's talk about the what did you come up with? So the slope is getting lower. Okay, yeah. So we got slope getting lower. What other possibilities do we have?
By the time it goes steeper and steeper and steeper.
So we got slope getting shallower and slope getting steeper. Yeah, so it may change along the length of the river, right? The slope, right? It starts out as constant, and so if we have something like this is our picture to begin with. I guess, can you see that at all over there? Yeah. So, yeah, where's it going to get steeper?
Well, at the start.
Yeah, right, so it's going to get a little bit steeper up here. And the question is, why might it get steeper there? Why does it need to get steeper in that area to balance the uplift?
Because there's sediment being deposited at the end of the bottom.
Yeah, so I mean, there's going to be some sediment deposited out here. We know that this is going to be shallower slope. But if you look at the equation that we have here, let's not worry about how the initial slope is constant to begin with, but over time, you're right, this part of the landscape where it's up high is going to get steeper. And the question is, why would it need to get steeper? If we assume that the idea is over time this will reach an equilibrium where there's a balance between the river eroding and the uplift, why would it need to get steeper in the high parts of the catchment? This steepness is compensating for something, if that helps. So what else changes as you go to that higher part of the landscape?
Well, there's not that much water we need.
Exactly. So as you go up higher and higher, the area gets smaller, or if you think of area as a sort of way of modeling how much discharge there is in the river, you don't have as much water there. So in order to have the same power to erode into the landscape, you have to make the rivers steeper. And you see this in natural landscapes. As you go, the steepest parts of drainage basins are usually up at the highest elevation where there's very little water. Now, you could also say that those are places where maybe bedrock erosion by the river is not as prevalent as landsliding or mud flows or debris flows or other things. But the point is, we end up getting something that looks like this over time. It becomes kind of this concave up shape where it gets steep up here because you have a low area. Down here you've got plenty of water. So the channel gradient doesn't need to be that steep because there's just enough power within the discharge of the river to erode, even though the channel is flowing at a shallower gradient. And if we look at models of how these kind of rivers erode using the stream power law, we see exactly that. That the higher elevation parts get steeper, and you'll see this in the exercise for this week, that you'll model exactly the same thing. And you'll see that up toward the high elevations, the river has to get steep, and that's just because there's just not any water there to do any erosion. So in order to erode, you've got to get the same small amount of water flowing over a steep slope to have the same erosion power. So so that's the picture. And what we see with the stream powers, it increases as you go downstream with the increasing discharge, and that the slope goes down to compensate for that increase in discharge, and that here the slopes are high. And you'll basically model something that looks actually quite a bit like this picture here for the exercise for this week. I think I'm going to skip over this recap since we've just had a little bit of time to talk about things. So our main differences between the advection and diffusion equations, I won't make you guys answer that question, but rather I'll just tell you that for the diffusion equation, we have the relationship between the change in elevation with time being related to the curvature of the landscape, or the second derivative of the elevation with respect to some horizontal distance. And that's compared to the advection equation, where we have the change in elevation with time being directly related to the slope. The other thing is that we worry about conserving mass with the diffusion equation, and we don't worry about conservation of mass for advection equation. And the special thing about the stream power erosion law compared to the general advection equation, essentially the only difference is that we say this constant c that we saw at the beginning is replaced by some terms that change as a function of space. So when you go along a river channel, you'll have things like the slope that will change along the channel, the discharge, and potentially the erodibility. I don't think we look at changing that in the exercise this week, but we could. There's nothing that would prevent us from doing that. And you'll have the code, so if you want to play with changing the erodibility along the length of the channel, you can do that yourselves. So that's our introduction to the advection equation. And now I'll just take you here for a second to the lesson for this week, and I'll just zoom in just a little bit. So we've gone through this set of the slides on the advection equation. There are also some notes here about solving the advection equation. These are optional, again, this week, and probably even less relevant to the exercise this week, because this is done for heat transfer equation in 1D. So if you're interested to see how you can solve the heat transfer equation with advection and diffusion in 1D, the notes are here, but there's nothing you need from these notes for the exercise for this week, unlike last week. So anyway, in earlier versions of the course where we had a bit more time in lecture, I would normally go through solving this on the board, but instead I've just put the notes here in case you're curious. So you can find different solutions to the heat transfer equation in 1D here. So that's that, and then that takes us now to exercise number 11. And for the exercise this week, we are basically looking at river advection, or erosion, using the stream power erosion law. And you're given a starter script like last week, and in fact the starter script works. So you can use that right from the start of the exercise this week. But I'm going to walk through a little bit of how this starter code is set up, because it is a little bit more complicated than the past weeks, and I'll show you why in just a second. So you'll take that, and I think, well, everything that's done beyond this point is just basically changing some of the parameters in the code. So we'll take a look here quickly just at what's in this starter script and what it models. So it is a a model of this stream power erosion law for an uplifting landscape, and it's essentially like this river channel profile view like what we were just looking at. And there's a couple things in here that are going to be new, and they're things that you don't have to code, but it's maybe good to kind of understand that they're here. So when the code runs this week, it's going to basically do an animation in the matplotlib window that pops up when it starts running that will show you how the river channel profile evolves through time. In order to do this in matplotlib, it's a little bit, not super complicated, but a little bit more involved. So I've set that part up for you, and what it means is there's a couple functions here that you should look through and just try to sort of read the comments and see if you can understand what's going on. You'll have to make some changes to one of them. It's not that big of a deal. But the two functions, one is called animate, and that just updates what's displayed in the plot window. And there's another function here called update topo that changes the elevation of the river profile through time. And so, animate is going to, basically just keep one plot window open and change what's displayed in the plot window. And so it actually calls this update topo function, and the update topo function looks at things like what the slopes are and then calculates this change in elevation dH dt using the stream power erosion law. And then there's a couple things in here that are just left as like, to catch anything nasty that might happen. So if there's any elevation for the topography that goes less than 0, it sets that elevation to be 0. If the elevations go negative in the topography, you can get the river to start eroding back in the other direction, and we don't want that. So you can break the code if you play with the constants a little bit, but it should work for everything that we'll do today. So we have this update topo, and again, I'd encourage you to read through and just make sure that you can understand what's happening here. It's a function, and you pass a whole bunch of stuff in there. So topography is just the elevation of the channel profile. dH dt is what comes out of here, but it also has to be used in order to calculate. It's used in here and recalculated there. And some other things like K, M, and the area, those different constants and things are passed in there. So that's the update topo function. Animate is similar kind of thing. We have these different parameters that are related to the plot window and to the plots that you'll have in matplotlib. So I'm actually going to skip and come back to what this animate function does in just a second. There's this section of user-defined variables. These are things that you're going to play with. Numbers you'll change, whatever, and it tells you in the exercise, which things change and what values to put in, so you can play around with that stuff. This just has different, things for how you set up the model to begin with to get it started, and just different, physical properties and whatever. So we define this channel profile. X is the variable that's used to represent the horizontal distance for the length of the channel, and then there's some uplift function that is used to determine how quickly the landscape is uplifting. There's different ways in which the topography can start out, so it can be a constant slope, like the picture we just drew up here, or it can be something that's like initially kind of a high, flat, plateau type surface. And so you have this little tag or flag in there for which one of those topographies you want to start with. But what I want to show you is the stuff related to the plotting. So down here we have stuff we normally use, like plt.figure, but you can see that I'm assigning that to a variable, and we haven't done that before. Normally you've just done plt.figure to get a matplotlib window to appear. Here we're assigning it to a variable called fig, and so this is so that we can refer back to that figure window later on. We do the same thing actually with the plt.subplot, we assign that to be axis 1. And so that allows us then to do certain things to that subplot window, like set what the x limit is for the axes, set what the y limit is for the axes. And I also then here have this plt.plot command that's assigned to a variable. The comma here is not something you need to worry about too much, but it isn't necessary to have this comma because I believe this plt.plot returns more than one thing, and we want to just make it clear that we only want the first thing that's returned there. But this plot1, by assigning this plt.plot to a variable called plot1, I can then later refer to plot1 to change things about that plot. Like if I want to update what data is displayed there, I can do that using this plot1 variable. Whereas before, I'd have plt.plot, the plot would appear, but I couldn't do anything to it after that point. It's just there. And the key to having the animation work is I need to be able to refer back to that plot that I made earlier and change what's plotted. So if you kind of follow that we're basically setting some variable to refer to the plot data and some variable to refer to the subplot window. Once these things are assigned, I can then go in and use this animation function that is here. And you can see that, for instance, plot1 dot set y data to topography. So topography is the elevation of the river channel, and here I'm just saying topography has changed because the first thing I do in this animate function is I assign a new variable or new value to topography and a new value to DHDT that comes from this update topo function. Maybe this is confusing, but essentially we just allow some time to pass, we change our river channel geometry, and we have to update the new elevations of the channel there. This plot1.set y data then just says on the y-axis, change the values that are plotted to be the new values that are in topography. It also changes the limit for the y-axis so that if the topography has gone up, that you make sure that you keep your plot window big enough that you can still see everything. And otherwise, then I put in some text to show how many years have passed and what the elevation is, and there's some other things in there. So, yeah, I would again encourage you to take a look through the code yourself and take some time to make sure that you understand at least what's going on in general. But those were the things I wanted to highlight because otherwise you're going to be a bit confused since we're doing some new things. You will see lots of examples of this kind of assigning a plot variable with this plt.plot command. If you look around online for people using matplotlib, you'll see it's very often done. We just didn't do it because it's simpler at first to just not assign anything to the variable, but just have the plots display when you use them. If you want to change the values that are being plotted, you have to be able to use a variable and refer back to which plot am I talking about and what data should change. So with that, then what I can do is I'll just show you what your code should do. But the exercise, you get the starter script, and when you run the starter script, if I'm in the right location, I think I am. I'm not in Spider right now, but I'm just going to run this from within IPython, and I guess that's probably pretty small. So let me see if I can make the text size a little bit bigger. How about like that? Is that a bit better? So I'm just going to run this river profiles.py code, and when it starts running, you'll see something similar. Oop, come here. Why are you going behind there? Basically, you'll see something that looks like this. And you can see here the text obviously is changing. It's maybe not that easy to see that this river profile is changing. So what I'll do is I'll just run this again from the start. And that's the time where the river profile is kind of changing the most. The landscape is being uplifted, and this river is basically carving its way into the landscape through time. So when you run the starter script, you'll get this, and that's your jumping off point for the exercise. Then you'll start changing some of the numbers, and you're asked some different questions about how the code works and things like that. So yeah, that's the exercise for the week. Are there any questions? Did you kind of follow how this river, bedrock river stuff works? I know it's not maybe that familiar, but did you at least kind of get the idea of how this stream power erosion works? Yeah, mostly. All right. So right now the code's set up to run for 2 million years. It takes about a minute, or maybe not quite a minute, on my computer to run. So when you start it up, it will not run forever, but it may take a little while to get to 2 million years of natural time. So just be aware, if you're using an older laptop or one that's not maybe that powerful, it could take a minute or two for the code to run for 2 million years of natural time. Otherwise, you're welcome to get started, and we will be hanging out here until around noon, and happy to answer questions and things like that.